Hello and welcome to our eOrganic webinar. Today, Dr. Kathy Soder will give her presentation called Supplementing the Organic Dairy Cow, Results of Molasses and Flaxseed Feeding Trials. My name is Deb Haliba and I work at the University of Vermont Extension as eOrganic's Dairy Team Coordinator. eOrganic is an online community of more than 1,200 ag service providers and farmers who are providing science, experience, and regulation-based certified organic information on the web. Together we publish articles, videos, and other content at eextension.org. This webinar is part of an ongoing series focused on certified organic dairy production systems. You can see more information about our webinars and view our other content on our website at eextension.org/organic_production. Okay, now it is my pleasure to introduce our speaker today. Dr. Kathy Soder is an animal scientist at the USDA ARS, or Agricultural Research Service, where she works at the Pasture Systems and Watershed Management Research Unit in University Park, Pennsylvania. And there she conducts a variety of research projects to evaluate the effects of diverse pasture systems on grazing behavior of ruminants and how farmers can use these systems to optimize forage and animal productivity. Kathy, thank you very much for joining us today.
Well, thank you. Let's see if I can get control of these slides here, get going. Welcome, everybody. And we do a variety of research. Some of it has been on the nutrition of pasture-based dairy systems, both organic and non-organic, but we're doing a lot more with the organic because of the pasture standard requirement for organic ruminants, particularly dairy cows. So today I'd like to discuss the results of some of this research that we have conducted on alternative supplementation strategies for organic dairy herds, including molasses and flaxseed. The molasses research we've been doing for a while, and it's pretty much completed as far as what we're going to do with it, and I'll be summarizing the results, but the flaxseed research is ongoing, so I'll have some preliminary data from that work, but mostly introducing some of the current projects that we have going on. There we go. So a few years ago, we started getting a number of calls from farmers and farm consultants on the use of molasses as the sole or primary energy source for grazing dairy cows, particularly in the organic sector. I didn't know a lot about molasses for organic dairy or for dairy cows in general at the time, but when we went to the literature, there really wasn't anything available that was relevant to grazing dairy cows in temperate regions like the Northeast. Therefore, it made sense that perhaps we should conduct some research of our own to help answer these questions that these farmers had. So we started talking to some farmers who were currently using or who had used molasses as their primary energy source. Some of these farms reported great success with molasses supplementation. However, we also heard of failures where cows dropped too far in milk production, lost body condition score, wouldn't rebreed, and these farms frequently went back to their feeding of corn or other grain sources. One reason for switching to molasses that was stated by the farmers was that in their instances, organic molasses was less expensive. It was available, particularly when organic corn was not available in the Northeast for a while, and it's in limited availability at times now as well. And but again, it was the expense. It was less expensive on a pound-per-pound basis than organic corn. There were also a number of farmers who believed that the molasses had 3 times the energy content of corn, and they were feeding accordingly. They were basically feeding 1/3 of the amount of molasses to the original corn level, and they claimed that that's where the real savings lie. However, there wasn't any scientific evidence to support this theory, and that really piqued our interest to see if that was really true. So there's been no real clear-cut explanation for the failure versus successes of our molasses in grazing dairies, so we decided to take this on as a research project. But first, a little bit of a background on molasses. Molasses is a rich source of sugars, particularly sucrose. This is in contrast to corn, which the energy source is primarily starch. The sugars are more quickly degraded in the rumen, and this can be good or it can be bad. Compared to the starch found in corn, sucrose has been shown to enhance the net yield of microbial protein synthesis. Not only does this mean greater numbers of microbes in the rumen that can digest feed, it also means greater amounts of microbial protein that's passed to the lower gut of the animal to be absorbed directly by the cow. Sucrose can be beneficial in that there may be more synchronous energy release of highly degradable protein that's found in pasture. That means that when the pasture protein is being broken down, the energy is available at that time when the bugs need it. Other sources of energy, such as corn, may degrade more slowly, so there's kind of a lag time between the time where it hits the rumen and the energy is available. So depending on when it's fed in relation to the pasture consumption, it may or may not be readily available to the microbes when they need it the most. So the synchrony may result in the rumen microbes capturing greater amounts of that pasture protein into microbial protein rather than excreting it as urea, which is an energy cost to the animal as well as an environmental issue. And this has been shown in confinement situations when molasses was used in place of high moisture corn, where it reduced ruminal ammonia and urinary nitrogen excretion. However, we can get sugars too high where it impairs ruminal function, so care must be taken not to exceed those levels. But there have been some real train wrecks where cows have lost significant body condition, milk production, and wouldn't rebreed. These failures cannot be pinned on any one reason, making it very difficult to predict under what conditions molasses supplementation may be successful. Additionally, there's no research to support that 3-to-1 ratio theory of molasses having 3 times as much energy as corn. The National Research Council lists molasses as having very similar energy content to corn. However, the type of energy source, that sucrose versus starch, is different, which may be where this is coming from and may impact ruminal fermentation. Of the research that does exist on molasses supplementation, there's limitations on applicability to the Northeast grazing dairy systems. Molasses was not fed at high rates like it is in some farms in the Northeast. It was not fed to grazing dairy cows. It was mostly beef cows on Western Range or dairy cows in confinement. And in the literature, it was found to be fed in combination with another source, either grain or a urea source or something else, not just molasses as the primary supplemental energy. And much of this research is also quite dated, from the 1950s and 1970s, and many factors, including the feeds, animals, and management, have changed since that time. As mentioned previously, molasses can pose a number of problems. The high sugar level shifts microbial fermentation, which can reduce in greater production of lactic acid compared with starch, which can decrease ruminal pH and ruminal fiber digestion. Starch has a slower rate of degradation than sugar, which again may impact fermentation in the rumen. Additionally, starch produces more propionate than sucrose. Propionate is an important volatile fatty acid produced in the rumen that's utilized by the ruminant as an energy source, analogous to the glucose in humans as an energy source. The high levels of soluble protein from pasture produces high levels of ammonia, which is toxic in the rumen, and as I mentioned earlier, it's converted to urea and excreted in the milk and urine. But this is not only a waste of nutrients, because this urea could have been recaptured as microbial protein and utilized by the microbes and the animal. It can cause environmental concerns and result in impaired production, including loss of body condition, breeding performance, milk production, acidosis, and laminitis. So we tried to answer some of these questions we were receiving regarding molasses supplementation using a 3-pronged research approach. First, we conducted a couple of in vitro or in the lab studies to evaluate the effects of molasses supplementation on ruminal fermentation. Secondly, we conducted a 2-year on-farm observational case study on an organic dairy farm that was using molasses as its primary energy source. And finally, we conducted a more controlled cow study with the University of New Hampshire's organic dairy herd. So, since most farmers were using it as a corn substitute, our first fermenter study compared the use of molasses versus corn meal in pasture-based diets. So we went to our continuous culture fermenter system. In essence, those are artificial rumens. We can inoculate these fermenters with rumen fluid from a cow and then basically feed the fermenters various diets and measure the products of that fermentation, including nutrient digestibility, ammonia, volatile fatty acids, pH, and bacterial protein synthesis. While the system is far from perfect, it does allow us to screen treatments and get detailed information on ruminal fermentation before moving on to larger scale, expensive cow studies. For our first experiment, we compared molasses with cornmeal, and our treatments were: we had an orchard grass only diet, which was basically our control diet, and then we fed molasses at 5% of the total dry matter plus pasture, cornmeal at 7% of the diet plus pasture, and the difference was because there was a little bit difference in energy content, and we were trying to maintain the same total energy level, so there was a little difference in how much we fed. The fourth diet was a combination of molasses and cornmeal at the same levels as above, plus the pasture. And for the measures of ruminal fermentation, we looked at ruminal pH, volatile fatty acid production, bacterial nitrogen efficiency, nutrient digestibility, and nutrient utilization. Let's first look at nutrient digestibility. Across the x-axis at the bottom of the screen, we have our 4 treatments: the pasture only, the molasses, the cornmeal, and the molasses plus cornmeal combination. And we evaluated dry matter, which is in the blue bars, neutral detergent fiber in the red bars, and crude protein in the green bars, digestibility. While we had no changes in the dry matter or fiber digestibility, when we look at the green bars, protein digestibility was highest for the molasses diet and lowest for the all-pasture diet. Additionally, protein digestibility may have been lower for the two diets containing corn compared to with the molasses diet due to the fermentable carbohydrate of the corn impairing digestion of the protein. The take-home message is that both supplements increased protein digestibility compared to the all-pasture diet, with molasses being slightly higher than the cornmeal. Additionally, the combination of molasses and cornmeal performed similarly to the cornmeal diet, suggesting that at these low levels of supplementation, the small amount of starch did not show any added benefit. If we take a look at the ammonia concentrations, that was lowest for the molasses plus the cornmeal diet. This was probably because we were substituting more of the high-protein pasture for a lower-protein supplement rather than being an actual effect of the supplement impacting ruminal fermentation. So we don't really attribute that to the molasses or to the corn. If we look at bacterial efficiency on the left, and this is defined as a proportion of substrate that is utilized by the microorganisms, it was not affected by diet, suggesting that microbial populations were not significantly affected. So we didn't really shift populations or shift the efficiency of those bacterial populations. Likewise, the production of volatile fatty acids, which are important byproducts of the rumen because the animals utilize those byproducts for energy, milk fat production, and a lot of other important body functions that so we're always looking at volatile fatty acid production in the rumen. These were not altered by diet, further suggesting limited or no shifts in microbial populations and activity. In summary of this study, molasses responded fairly similarly to cornmeal in improving nitrogen utilization in the fermenters. Both supplements provided only minimal improvements over the all-pasture diet. So molasses is not a magic bullet fix compared to corn. However, it does show promise at these low levels of supplementation in providing a ruminal environment not unlike that of corn supplementation. However, even though we had this information needs to be taken to the cow level to evaluate the whole cow effects, including milk production of molasses supplementation, and we did get to that here in a little bit. But first, we had another question that we wanted to answer with the fermenters. We conducted a second fermenter study related to molasses. When looking in the literature, it seemed like there were a lot of suggestions of an interaction between forage quality and level of molasses supplementation, which may also help explain the variable responses observed on individual farms. To put it another way, there may be an interaction between forage quality and molasses supplementation that may result in differences in ruminal fermentation. So we decided to look at this potential interaction and developed a fermenter study to look at high and low pasture quality. So we had two diets with high, what we call good or high quality pasture, two with lower quality pasture, and then we fed molasses at two different levels, at 5% and 10% of the total amount fed. So we could look at the interactions between these two. So we took a pasture, and it was an orchard grass pasture, a little bit of leguminate, mostly an orchard grass pasture, and harvested it at 2 weeks and 4 weeks regrowth during the active growing season to mimic grazing scenarios and different forage quality. So this good quality pasture would have been at the 2-week post-harvest, and then the lower quality would have been another 2 weeks regrowth for a total of 4 weeks of regrowth. So as you can see from the 2-week regrowth, the crude protein, the rumen degradable protein, we jump down to the starch, and the water-soluble carbohydrates, which is an energy source, are higher than in the lower quality forage, which is not surprising because it was at a more immature state. We're going to have higher nutrients in it. And at the same time, the fiber, the neutral detergent fiber, was lower. And then the net energy for lactation was higher. So we did see some differences in it. It's not the extreme forage quality differences that are noted in the Western Range papers when they get into some extremely low quality forages, but it was quite representative of what we see in Northeast pastures that could be impacting response to molasses. Taking a look again at nutrient digestibility with dry matter in the blue, NDF, neutral detergent fiber in the red bars, and in the green bars we have crude protein digestibility. This chart, and it's similar to the last chart as well, the only digestibility difference that we noticed was with dry matter, and even that was subtle. It was statistically different, but not really great. But this was an effect of forage quality, because if you look, we have the two low quality, the L stands for low quality forage, G for good quality forage, and then we have the 10 and 5% molasses treatments within this two. And the two lower quality forages had slightly lower dry matter digestibility than the good quality forage, which is not surprising. We're going to have a little bit more fiber, a little less digestibility, a little bit less availability. So it was more of a forage quality effect than it was a molasses effect. Looking again at ammonia concentrations, and while they weren't affected by the supplement, there was a tendency for lower ammonia concentrations in the lower forage quality diet, which means it was, if we'd had more data or had a little bit more differences, it would have come up as statistically significant. But this is probably a result of lower nitrogen intake because there was lower crude protein content in the lower quality forage, but no molasses effect. Bacterial efficiency, same as before, looking at how well at the bacterial productivity was not affected. So there were no major effects on that based on molasses supplementation or on the quality of the forage. So there were no effects either way. However, volatile fatty acid production was lower with the lower quality forage, again, in response to the lower forage digestibility. So in summary of the two fermenter studies, there were no significant interactions between molasses and forage quality in this most recent study. In the first study, molasses did not impact ruminal fermentation either alone or in combination with cornmeal. So farmers that are using molasses successfully must consider that other management factors may contribute to the success of molasses, including timing of supplementation, if they're feeding it before or after a grazing session, and how long before or after a grazing session, because it can make a big difference if it's fed, any supplement is fed immediately before they go out, or if there's a lag time. If your first cows come out of the milk parlor and they're not going out to the pastures for 2 or 3 hours because you're waiting for the rest of them, or you're holding them in to breed them or do a preg check or something like that, can affect how the rumen digests and ferments supplement and how the body responds to it. The molasses source, there's different sources, beet, sugar, there's 2 or 3 different sources of molasses. They're going to have different nutrient contents, different mineral levels, different protein and energy levels, so that can significantly affect the response to molasses. The level of molasses supplementation, our treatments weren't extremely high. They've been higher, they've been lower, so there's a lot of variability in what's being fed out in the field. The adaptation of the cows to a molasses diet, if they're coming off a fairly moderate or high corn diet and they're still going on molasses, there's going to be an adaptation period until they're ready and adapted to the molasses diet. And then forage quality can still affect it, even though we didn't have extremes. If you get a lot of extremes in forage quality, you may still have some impacts. So the next thing we did is one of the farmers that we had been talking to agreed to serve as a case study for us. The lab work was great. It provided some preliminary data, but it's obviously not a cow. So this project was a cooperative effort between myself, Karen Hoffman of the USDA NRCS in New York, and Larry Chase at Cornell University. We conducted a 2-year grazing study in 2008 and 2009. It was an observational study. We are not asking this farmer to do anything differently other than what he was doing anyway. We were just observing what was happening, what his feed changes were, what his pasture and feed quality was, what the milk production and milk composition was doing. But he was in central New York feeding molasses successfully for a number of years. In 2008, he fed 3 pounds of molasses with 1 pound of cornmeal barley grain mix. In 2009, he adjusted the ration based on his observations of body condition score and milk yield the previous year, both of which were lower than he would have liked. While he made several adjustments during the grazing season as noted in the slide, in general, he reduced the molasses feeding to between 2 to 3 pounds per cow per day, depending on season and other factors, and increased the grain mix to 2 to 3 pounds. Data was collected during the grazing season. The farm consisted of 80 acres of orchard grass, white clover, red clover, and forbs pasture. In 2008, the herd consisted of 56 crossbred cows. In 2009, the herd had increased by 10 cows, primarily due to a number of first calf heifers entering the milking string. And the herd was a seasonal calving herd, calving in the springtime. The data was collected included body condition score on the cows, milk production, milk composition including fat, protein, somatic cells, and milk urea nitrogens, and pasture samples were collected and analyzed for nutrient content. We did this monthly throughout the grazing season for both years. In addition, we collected some economic information related to income over feed costs. And then finally, the Cornell Net Carbohydrate and Protein System model was used to see how well the model predicted milk production of the herd based on descriptive parameters that were entered, including animal factors, environment, activity level, and diet quality. And just as a note there on that previous slide, he did pour the molasses over that cornmeal grain mix to slow the intake of the molasses. Body condition score numerically averaged 2.5 in early May for both years, which was approximately about 40 to 60 days in milk for most of the herd. At the lowest point, body condition score averaged 2.1 in 2008 and 2.2 in September of 2009. The later nadir in body condition score in 2009 may have been due to cows maintaining condition later into the season, possibly due to the greater supplemental starch levels. In both years, body condition score then increased to 2.6 in 2008 and 2.4 in 2009 by October. Due to the current study beginning in May rather than March, that's when we started collecting our data, the body condition of the cows during the dry period was unknown, as well as how much body condition they had lost from calving to early May. However, the rate of condition loss did not appear to be as rapid as would be expected based on National Research Council nutrient composition data for molasses. These book values would predict that less energy was being fed during early lactation, resulting in greater condition loss. However, the cows were significantly past their peak production when the lowest body condition scores were recorded. Milk production followed a typical lactational curve for a seasonal calving management system. Peak production occurred in the middle of May at 52 pounds of milk per cow both years, and wasn't different between years, and then gradually declined through the rest of the study period. Production in November was about 25 pounds per cow, which is a persistency rate decline over the 6-month period of 12% per month. And if we break that down just a little bit, looking at that persistency, the rate of decrease in persistency between late May and early July was greater than expected at 25% per month. And this was likely due to the lower pasture quality during that time in 2008 and lack of dietary energy around peak lactation both years. The overall decrease in persistency is greater than what typically seen in multiparous cows under either year-round or seasonal calving management. The persistency rate from peak milk production to 6 months is generally 93 to 97%, with a decline of 3 to 7% per month for first lactation animals, and 91 to 96% with a decline of 4 to 9% per month, rather than that 25% that we observe for both grazing and non-grazing cows enrolled in DHI in New York. Not unexpectedly, milk fat increased as lactation progressed, ranging from a low of 4% to a high of 5.5% at the end of the grazing season each year. Milk protein averaged 3.4% in 2008, but it was greater in 2009, averaging 4.3%, which may have been a result of greater starch in the diet, resulting in lower ruminal ammonia concentrations and greater microbial protein synthesis. In both years, the milk protein increased from spring to fall as lactation progressed in the herd and the milk production declined. Other solids, which weren't shown here, were similar between years. Such changes in components are typical in seasonal calving herds as the stage of lactation progresses. Furthermore, by October, the cows were being fed a fair amount of dry hay or baleage, which would help increase the percentage of milk fat. Milk components may also have been influenced by the greater percentage of first calf heifers in the herd in 2009 compared with 2008. The milk urea nitrogen levels were relatively high throughout the grazing season, as would be expected on a high-protein pasture diet with low levels of non-fiber carbohydrates, or lower energy, the ratio of protein to energy. The recommended range for milk urea nitrogen is between 8 and 12, which would be in this range, if you can see the cursor. And the herd averaged 16.2 milligrams per deciliter in bulk tank samples both years. The lowest MUN level was in late May at 9.7 in 2008 and 9.2 in 2009, when pasture protein levels would be expected to be the greatest. However, in 2008, the pasture was lower in crude protein in May and June than what is typical due to overmature forage being grazed. Basically, the pastures got ahead of them and they were still grazing them, so it was overmature. In 2009, pasture protein was greatest during the comparable time period in the mid-20s. I've got some additions there. We'll skip through that because we went through that. All right, the relationship between milk urea nitrogen and pasture protein is shown here. You can see the milk urea nitrogens in the blue line, and then those maroon bars is the percent protein at those time points when we took the samples. Once the pastures were clipped and returned to a vegetative state growth in late of June of 2008, pasture crude protein levels remained high throughout the remainder of the grazing season. As the season progressed into the fall, the relationship between pasture protein and milk urea nitrogen was weaker. We had a lot of more dichotomy between the two during the main part of the grazing season. But again, they were being fed some baleage and hay, which is going to change that. So they were fed dry hay for half of the day each day beginning in late September, which reduced the total protein in the diet. Forage quality was generally high. We have the months through here, May through October, and then we have dry matter, neutral detergent fiber, crude protein, and then we broke it down to soluble protein. But it was higher throughout the grazing season, except in the spring of 2008 when the forage was more mature due to the rapid growth rates under ideal growing conditions for cool season grasses and legumes. The crude protein levels above 20% are typical for our cool season pastures, as are the neutral detergent fiber levels below 48%, so it was a very vegetative pasture. Pasture non-fiber carbohydrates. Non-fiber carbohydrates include simple sugars, starches, and soluble fibers, and then we can break it out into the starches and this is ethanol soluble carbohydrates, or the sugars. Were of interest due to the high level of sugar in the diet from molasses and the low level of starch from grain. The year did not impact any of these components, and in general, the sugar, the ESCs, decreased as the grazing season progressed, while the NFC, non-fiber carbohydrate, and starch were not affected. So just for reference, if we're looking at what's recommended through the NRC, the National Research Council, NFC is usually recommending 38 to 44%, so we were deficient in that based on NRC. Starch is usually recommended around 25%, so we were really, really low in starch. And then the sugars are recommended between 4 and 7%, so we were a little bit high on some of those. In October, there was a decline in nutrient content with shorter day lengths, not as much photosynthesis, and not as much sugar in the forages. During those times, energy may have limited milk production more than other times during the grazing season when NFC and ESC were greater. Therefore, despite adequate forage availability, energy intake was likely reduced during this time. When the diets were analyzed with the Cornell Net Carbohydrate and Protein System model, they were described as a 1,000-pound, second lactation animal, mixed breed of Jersey, Brown Swiss, and Holstein. Milk production, milk components, and body condition score were entered at the levels that existed on the sample day, and environmental factors such as temperature, humidity, wind speed, distance walked, and activity were documented by the observer as close as possible to the actual conditions that existed on that sample day. Pasture quality and estimated intake, molasses, and grain fed were entered into the ration portion of the program. The model provides estimates of the metabolizable nutrient, and that nutrient can be a lot of things. Most commonly, we're looking at energy, protein, or specific amino acids, and I want to concentrate on the energy and the protein. So it's providing for the metabolizable, that amount of energy allowable milk, how much of that nutrient is available to produce milk. So what this means is it will predict how much of that nutrient is available for milk production and which of those nutrients is first limiting. That will be the one that first limits milk production. So for the current study, the results are primarily focused on the difference between actual animal performance and the model predictions, although some values such as MUN will be discussed as well. If we look at, we have May, June, and July, and the next slide will have the next couple of months. I couldn't fit it all in one slide with the year, and this is what the actual milk production was on the day of sampling. And this is these next 4 columns, the last 4 columns, are what the model would have predicted for milk production. And so if you take a look at particularly in May of both years, the model predicted that energy would be the limiting nutrient for milk production and that metabolizable energy was deficient. However, the cows exceeded the prediction for energy allowable milk in May for both years. This may have been due to some cows carrying more body condition and early lactation than those that were scored, thus allowing for more energy from the body reserves to be used for milk production, or the cows consume more pasture than the quantity is assumed in the model. The CNCPS was designed for confinement systems, has been adapted to pasture, but there may still be some tweaks in the model that need to be made. These are the next 3 months. In August of 2009, the ME allowable milk was 1/2 that of actually, the cows produced twice as much milk as what was predicted by the model. And this appears to be due to unusually high lignin value in the pasture. Lignin is a fiber component that's pretty unavailable to the animals. By the time that this was discovered, the sample couldn't be retested because it had been discarded. So we chose to keep the value because we didn't have a sound basis to adjust the lignin value. So the model did actually predict ME allowable milk for the other months. Cow performance was generally lower than model predictions. But these models are only as good as the database that it uses. Since data is so limited on molasses with pasture systems, caution must be advised in interpreting these results. However, they do still provide us with a baseline on which to predict productivity. Again, in October, there was some hay and baleage fed, so it was higher than predicted, but they may have been consuming more of one factor over another, either more pasture or more hay than what we had plugged into the model, since we couldn't exactly measure what they were consuming. The model over-predicted milk urea nitrogen in May, June, and September. September's on the next slide, but it'll give you, it's the same type of result, by a range of 11 to 21 milligrams per deciliter. When actual months were higher than what the model predicted, the cows may not have been as efficient at utilizing the pasture protein as the model expected. However, the milk urea nitrogen prediction in the model was driven by the relationship between that protein supply and the ruminal ammonia balance, and is less sensitive to shifts in energy fractions. So that might have been protein driving this, not the energy, and protein was not limiting in these diets. So if we look at nitrogen excretion, we got it, there we go, was greater than 100 grams per day from June through September of both years. Excess nitrogen from pasture containing high levels of rumen-degradable protein result in increased ammonia levels, and the ammonia, which is toxic, is either reincorporated into microbial protein, or it enters the bloodstreams, transported to the liver, converted to urea. This conversion of ammonia to urea requires an energy input that could be used to direct milk production or maintenance, and may have contributed to the continued loss of body condition through August. The excess urinary nitrogen excretion may also be an environmental concern, and that uneven deposition of urine in his hot spots on pasture may result in significant localized nitrogen losses by volatilization. And this slide is just a continuation of the previous slide. You can see even in August and September we got high nitrogen losses. So although some farmers report good success with feeding molasses to lactating dairy cows, it appears that there's opportunity to feed more energy and achieve greater milk production in this herd. A greater level of starch may provide enough energy to improve the energy allowable milk. Greater starch levels may also improve utilization of pasture protein, reducing nitrogen excretion and urea cost. The slightly greater starch intake due to the increased grain in 2009 in this study did not appear to be enough to additional starch to make the difference, so we'd have to look at maybe different levels or higher levels, but you also have to factor in a cost-benefit ratio. Income over feed costs was greater in 2008 when more molasses was fed because of the greater amounts of molasses and the lower cost of that molasses. Average daily feed costs remained fairly constant across the grazing season in 2009. Therefore, the primary influence on decreasing income over feed costs within year was the decreasing milk production of the seasonally calving herd as the grazing season progressed. Milk price was approximately $1 per hundredweight greater in 2008, and feed costs were greater in 2009 due to the increased cornmeal feeding and the increased cost of that corn. But the grain price itself was lower in 2009 than 2008, and it wasn't quite offset by that change in molasses supplementation. Because body condition score and reproduction were similar in both years, feeding less cornmeal resulted in better income over feed costs, resulting in an average of 96 cents greater income over feed costs per cow per day in 2008 during the grazing season compared to 2009. The cost of organic corn in comparison to the cost of organic molasses would need to be evaluated both individually and in combination with various feeding rates, as the interest in the use of molasses is partly due to the greater costs of organic grain. Further, the potential increases in milk production would need to be predicted with the model on a case-by-case basis. So finally, we looked at a controlled study with the University of New Hampshire's organic dairy herd. And this was in collaboration with Andre Brito and his staff there. And again, we were comparing cornmeal with molasses on milk production, milk composition, and nitrogen metabolism of the organic herd. So what we did here is we split the herd into two groups, and they were fed a pasture diet. They did receive baleage at 18% of their total dry matter intake, and we top dressed that with molasses or cornmeal. The cornmeal was actually fed in a tub beside the baleage. You can see the tubs here, but the molasses we poured onto the baleage to increase consumption because they weren't really licking it out of a tub. We collected a lot of data that you can see here on milk yield composition, a lot of metabolites, blood metabolites, urine, body weights, body condition scores, grazing behavior, and then a lot of pasture sampling as well. The cows were grazed separately in groups by treatment so that pasture intake could be estimated, except for milking time when they were brought into the barn twice daily. So they were out on pasture about 20 hours a day and then brought into the barn for milking and then for this individual feeding. After milking, the cows were individually fed their supplements using kaolin gates. Each cow had a transponder around its neck that only allowed it to enter one kaolin door to access its feed, so nobody else could steal feed from anybody else. The cornmeal was placed in tubs and the molasses was top dressed on the balage. We took a lot of pasture sampling. We were trying to estimate dry matter intake, pasture intake of the animals, because that's very, very hard to quantify. We were using a rising plate meter, doing a lot of clipping before and after grazing to try to quantify forage available, forage utilization, and forage consumption, botanical composition of the pastures, and then, of course, the nutrient quality. A couple of quick slides on some of the preliminary results of this study because we don't have it completely analyzed yet. No statistical difference in milk production between cornmeal and molasses supplemented cows. However, numerically there appears to be a slight increase in milk production with the molasses. If more of the variation could have been controlled, for example, if we had more cows per treatment, or we may have been able to see if that was actually an economically significant difference or not, but they were producing a couple pounds more milk, but from a statistical standpoint we couldn't say that it was different. Looking at pasture intake, again, not statistically significant, but based on our estimates, the molasses supplemented cows were consuming a few pounds more pasture per day. But again, our pasture intake is estimates of estimates of estimates with a lot of variation and a lot of potential for error. We don't have a good way to, we can't go out and weigh pasture out, let the cows eat it, and weigh it back. So we don't have a really great way to look at pasture intake, so we take these estimates and go by that. So we work with the data that we can, and these are fairly close, not statistically different, but it appears that they work. But the supplement we can weigh. We could weigh it before and weigh it back. And the molasses supplemented cows were consuming more supplement, more of that baleage and more of their molasses. Now the corn wasn't an issue, but we think maybe the top dressing of the baleage was causing them to consume more of that baleage, because sometimes there were some refusals. And if we look at a percentage of total, no statistical differences there. No differences in milk components. Between the two treatments, milk fat averaged 4.8%, while milk protein was 3.5%, and this was with Jersey cows, so give you an idea of what breed and size of cows that they were. Additionally, body weight changes were similar between the two treatments, so we didn't see anything significant there. The milk urea nitrogens and the plasma urea nitrogen, you can concentrate on the MUNs because the urea goes into the blood, which is where we're getting it out of the plasma for measurement, but then it's being excreted either into the milk or into the bladder for excretion from the body. But it was greater in cows with supplemented with cornmeal compared to the molasses cows, with cornmeal being red and the molasses being blue. So there was a difference there, so there might have been some differences in nitrogen efficiency in those molasses supplemented cows compared with the corn. So we have a lot of ongoing analysis with this study. It's not published yet. We don't have it all out yet, but we are finishing it up. We'll have it out later this year. So we're looking still at the fatty acid composition of the milk, looking at some other factors, including the grazing behavior. Did they graze differently because of the supplementation? The pasture data is still being analyzed, and of course we're doing the final statistics as well. So that more or less sums up our molasses research that we've conducted. Again, you know, it's certainly an alternative to corn. It's not any magic bullet and needs to be used with caution and watching the cows and watching your milk production, your body condition score, that can be used as an alternative whenever corn is not or an option or may not be desirable for whatever reason on a farm. So application to pasture diets. So what can we take home? First, there's a lot of variability in response to molasses that appears to depend a lot on farm factors, including forage quality, molasses source, other supplements, and delivery method. Greater supplementation levels may be warranted, but care must be taken not to exceed thresholds to impair ruminal function, and the cost and ease of handling of molasses must also be considered. So now I'd like to shift to some of our flax research. We have a couple of continuous culture fermenter study, or a study that has been completed, and then I'm going to just briefly discuss some of our ongoing research. So another area of research was, again, came from the farmers. We started getting calls on this, didn't know a lot about it in relation to pasture-based diets. And it was in relation to oil seeds such as flaxseed. So again, we developed a research program to try and answer these questions. And our first step was to go to the fermenters to allow us to screen some treatments, and I'll present some of that data now. A little bit of background on the flaxseed. There's many potential benefits to flaxseed. First, it's rich in omega-3 fatty acids and alpha-linoleic acid, which has been found to increase as beneficial fatty acids, the CLAs, the conjugated linoleic acids and such in the milk, that may provide some health benefits such as anti-carcinogenic factors for humans. Second, flaxseed has been shown to decrease methane in cows fed conserved feeds in the barn. Low grain or high forage diets have been shown to favor methane production, so finding supplements that reduce greenhouse gas production while providing other positive attributes would be beneficial. However, while flaxseed is available in organic form, it hasn't been evaluated in pasture-based diets, and its availability can be limited in many areas. So we developed the fermenter study with the hypothesis that replacing pasture with incremental levels of flaxseed will reduce methane without impairing ruminal function. So as before, we went to those lower cost fermenters to screen our treatments, because if we get to a level of flaxseed that kills the rumen, it's a lot easier and a lot less paperwork to kill one of these fermenters than it is to kill a cow. So it's really nice to go to these and look at screen treatments so that we can take something realistic to a cow level and do a very valid study with limited funds. The diets that we used, we had a pasture-based diet, and we supplemented it either with no flaxseed, so it was an all-pasture diet or a control, and then we looked at 5, 10, and 15% flaxseed as a percentage of the total diet. As flaxseed, and we look, and again, look in the red bars is organic matter digestibility, and the blue bars is fiber digestibility. As flaxseed supplementation increased from 0 to 15% from left to right across the screen of the total diet, nutrient digestibility decreased. This may be partially explained by the substitution of lower fiber concentrations in the flaxseed as it was substituted for pasture, so we're having less fiber to start with. But this impact must still be seriously considered in overall digestibility of diets being fed to cows and the impacts on feed efficiency and productivity in the animal. As flaxseed of the diet increased, methane production significantly decreased. There were no differences between the 10 and 50%, so between the 5 and 10% was that threshold where we didn't see any more decreases in methane production, but yet we still saw further decreases in digestibility at that 15% level. So this would be beneficial from an environmental standpoint, but since the digestibility did decrease as flaxseed increased, consideration must be given whether this would result in reduced milk production, which could result, if you're going to maintain the same amount of milk off of a farm, do you need more cows, and what does that do to your total methane output off the farm if you're keeping more cows on the farm? So with this preliminary data, a multi-location, multidisciplinary research project was developed to evaluate the effects of flaxseed supplementation on organic dairy production. Again, we've published this fermenter study and took that data to go for this other funding that I'm going to explain here. So we were fortunate enough to receive a large-scale grant to research this area. We received a USDA NIFA Organic Research and Extension Initiative grant. It's a multi-location, multi-discipline, multi-state project. So it's ongoing, and I don't yet have any research results, but I'd like to finish the presentation by introducing this project to watch for in the near future, because we will be putting results out in the trade journals and in the publications and peer-reviewed journals as we get results from this. So there's multiple components to this project, but I'd like to just introduce the flaxseed component so we can stay on topic and stay on time. So the primary investigator who received the funding directly was University of New Hampshire. We have many collaborators in this project. Andre Brito was the one who spearheaded this project and put a lot of it together with his colleagues at UNH, Dr. Richard Smith, Dave Townsend, and Kirk Broders. And you can see we've got a wide variety of expertise there to look at not only the flaxseed, but there's a ryegrass component as well. So some of these guys are focusing more on the ryegrass component of this project. At the University of Vermont, we have Dr. Heather Darby, Sid Bosworth, and Bob Parsons looking at various components. It's nice to have an economist involved because we would look at the economics as well as just the productivity, because I think oftentimes it's the economics that we're missing from a lot of our applied research projects. From the USDA, from our lab, we have myself as the animal scientist, and then we have two folks working on the ryegrass component, Howard Skinner and Sarah Gosley, who have expertise in agronomy, plant ecology, and other areas such that they're working on the ryegrass component and then the flaxseed as well. And then the two other collaborators in this project are the University of Maine, Rick Kirschbergen, and Faye Benson at Cornell. So the project involves 2 to 4 farms in each of 5 states, and the states are, as I mentioned before, Maine, Vermont, New Hampshire, New York, and Pennsylvania. It's a 4-year study to evaluate the effects of flaxseed feeding on milk production, milk composition, especially those beneficial fatty acids such as CLAs and omega-3s, herd health, and economics of organic dairy systems. Pasture diets have been shown to increase those beneficial CLAs, beneficial fatty acids such as CLAs. But for approximately half of the year, our organic dairy cows are fed conserved forages which do not maintain those high levels of fatty acids. Since flaxseed has been shown to increase the fatty acid content, the study will evaluate the effects of feeding flaxseed during the wintertime on these fatty acids. In addition to these potential benefits, flaxseed will provide an alternative source of energy to organic corn. Some of the milk processors are interested in marketing a beneficial fatty acid type of milk. So this may provide these producers with a potential value-added milk market. If we get those types of markets, we can produce, for example, high CLA milk year-round. We can do it on pasture in the summertime and flaxseed in the wintertime. So the study began last year with the initiation of 2 years of observational work. Each farm is visited twice monthly for collection of feed, milk, and pasture samples. During the first 2 years, we're only monitoring what they're currently doing. They're not feeding flax, they're feeding other things, and it's a variety of different things. And starting this coming winter, the cooperating farms will be feeding flaxseed for 2 winters, with data collection continuing through that period. We also have 2 farms who are a forage-only diet. They're feeding pasture during the summertime and conserved forages during the non-grazing season, and they're going to serve as our controls in comparison to the farms that are feeding flaxseed. So, in addition to that on-farm study, we have some controlled research that will be going on at the University of New Hampshire, again in collaboration with Andre Brito and his crew up there. So we're going to be looking at doing some winter feeding of flaxseed with their organic Jersey herd so that we can do more detailed data collection on those animals that we can't do on farms. So we have a little bit more control, can do more with those animals. So we're looking at, again, probably something like 0 to 15% or 0 to 10% of flaxseed during the wintertime. And we're also going to do a summer flaxseed study as well to see what additional benefits we can get if it's beneficial to feed flaxseed during the grazing season. And just to give you an example of what some of us go through with some of this research, this is an example of the equipment that we use. This apparatus was used for methane collection. The canister on the cow's back that's so intriguing to the other cow has been evacuated, so this evacuated canister draws air from that tube that you can see running from the canister down the cow's neck, and it comes around to the cow's nose. And there's a little sampler right there that draws air from the cow's burps and is continuously sampling her burps. It's very labor intensive, but it just shows how challenging some of this data collection can be, including obstacles such as that nosy cow. They got quite adept at assisting their sisters in escaping from the equipment, so it made our jobs even more challenging to keep the equipment on those animals because their friends were quite happy to have it hanging in the rafters, so to speak. So with that, I'm going to stop and turn it back over to Deborah, and we can start our question and answer session. Or
the first question is dry or liquid molasses?
A good question. I should have said that. It was liquid molasses.
Mm-hmm. And was the cost adjusted on a dry matter basis?
We did it. The farmers were doing it on a pound per pound as fed. We do have some values for dry matter as well, but they were substituting a pound for corn for a pound of molasses as fed.
Okay. Great, thank you. I'm just scooting right down here. Did you see was there a substitution effect, or were cows limited in pasture intake with the molasses supplements?
Okay, they were not limited in pasture intake because we were giving them about twice what we expected them to eat because we did not want to limit them for that purpose. And what was the first part of that?
a substitution effect?
Oh, I don't know that. Well, we didn't. Our problem was we didn't have a third group. What we would like to have had was a no supplement group, where there was a control, but there was no. We didn't have enough cows for that. But I think at those low levels, you needed to get, I think, into higher levels to see a lot of substitution effect, because it wasn't that high of a. We might have seen a little bit with the baleage because we were feeding that at like 18% of their intake, but I don't think due to the supplement, due to the corn, or due to the molasses.
Okay, thank you. What was the dry matter percentage of molasses? Was one of the questions here.
Oh, that's a good question. I'd have to look it up in one of the papers.
And just note, I did. There was a summary of these molasses feeding studies published on the NRCS, New York NRCS website. So that's in your chat box to everyone, so you can see that fact sheet. There might be that information in there.
I'm looking up the dry matter as we talk, so.
Okay. I'm just going to go through and ask all the molasses questions first, just so we can kind of keep organized and not go back and forth. So one of the other questions is, on the New York molasses study, how did body condition differ with the corn versus molasses?
Well, we didn't see differences. I mean, with the New York study, it wasn't corn versus molasses. I mean, it was differences in years, but he also had a lot more first calf heifers that second year, which is going to impact the results. Because they're going to they condition differently, they're going to milk differently, they're going to be a little bit different. But we didn't see any differences between years. But we can't compare corn versus molasses in that study because we didn't do just corn versus molasses.
Okay, great.
Let me go back to that dry matter. Looking at our one study, it was 70.9% dry matter.
Okay, thank you. Thanks for answering that. Okay, so regarding the molasses, how easy was it to find certified organic molasses? And what's the range in, what's the range in cost? Do you have a sense of?
Well, I don't have current costs because these studies are 3 to 4 years old, so I don't want to go to cost now because I know so much has changed because we haven't done this work for a while. It was not difficult to source. In fact, I think UNH may have had it donated, but I'm not certain of that. Oftentimes with research we'll do that, but with the, I mean, I can find it here, so in the Northeast it's not that difficult to find. Okay. Other regions of the country I can't answer for.
Okay, and then in the Northeast you might have been dealing with some temperatures, so how well does molasses feed during the winter when it can be in the negatives?
Well, that's what I said. You talk about flowing like molasses in January. The thing that this farmer, it's going to flow slower in July. And if you're top dressing it on something like baleage or even corn meal, you may get more clumps. It's not going to flow as freely. And in the summertime, he has issues with flies.
Right.
So those are some issues with it that need to be dealt with, and especially on organic farms when you don't have a lot of options for fly control like you would on a conventional farm.
And then what kind of molasses were you using? What's the sort? Is it, I have sugarcane, dates. Do you know?
It was, Andre's probably on here could answer this. It was his stuff. I think it was sugar beets.
Okay.
So it was sugarcane or sugar beets. It wasn't dates.
Okay, and so if there is anybody from UNH, maybe you could chime in and just put something in the chat.
Yeah, there you go.
I don't see Andre on there, but okay. So did timing of the feeding of molasses affect the digestion parameters?
Well, we didn't test timing. What we would have had to have done, either with the cow trial or with the fermenters, was feed it at different times in relation to the pastures, and that could have been done, but we didn't do that. Ours was, we were feeding like they would on the farm, feeding the molasses basically before they went back out on pasture. So they were with our studies, we were feeding molasses an hour or so before they went back out on pasture. If you were feeding pasture first and then molasses, it could be a whole different story, but I don't have any data on that to say for sure. Okay.
And then one person that chimed in and provided some cost here. So currently corn is between 34 and 35 per 100, and molasses is about 45. So okay. just to give you folks a comparison.
Yep. Thank you.
Okay. Yeah, thanks. So this person says the Dairy Forage Research Center in Wisconsin has demonstrated that rumen biology is unique to each cow, and they were wondering if could cows be demonstrating a response simply have different sets of bacteria.
Absolutely. I mean, it's been shown that if you take the rumen contents out of 2 cows and swap them, and you quantify what the bacterial content of those cows, and you give them an appropriate period of time, it reverts back to what that original cow had. So there is a lot of individual cow-to-cow variation, and that in part is why we need so many cows per treatment, because of that variation. And it may also help explain for some of our systems why some cows excel in our systems and other ones fall apart. That we need to select for those cows that are adapted to our systems, and that may be one of those many keys to why cows are adapted to some systems and not others. So that wasn't really a specific molasses question, but it's more of an adaptation question, I think.
Mm-hmm. And this question might be related to that. So you conducted this research with Jersey cows. Do you think you might find the same results with other breeds of cows?
I mean the on-farm was mixed breeds. It's hard to tell. Yeah, so the New York farm was mixed breeds. So he had a variety of breeds on his farm, mostly crosses. But I don't know. I think it all goes to adaptation, but I'm not going to get into a breed argument over which one's better, which one adapts better. I can't answer that straight up.
Okay. And I'm just looking through the queue here, and I'm not sure I'm seeing any more molasses questions. If folks do have more molasses questions, this would be a good time to quickly type those in.
We can jump back and forth.
Yeah. Let's move on to flax for now, though. So the first question that came in was why flaxseed versus a meal?
Because the whole flaxseed has the oils in it, when the meal has had the oils extracted from it, and it's the oils that we're interested in stimulate or in changing the composition of the milk.
Okay.
And it's also going to have a higher energy level.
Okay, great. And what was the maximum amount of flax fed?
In the fermenter studies, it was 15% of what would have been fed to the fermenter, 50% of dry matter intake. Okay, great.
And then, did you again the source of the flax? Was it ground at all, or did you just feed the whole seed?
That's an important point. With the cow studies, with the fermenter studies, we had to grind it because we don't have a cow to masticate or chew it. So we had to grind it for the fermenters. But with the cow studies, we're going to be feeding whole flaxseed, and that is in part because when you crack or grind that flaxseed, it oxidizes. The shelf life isn't real long. So you can't get a whole tractor trailer load in and keep it in the bin for months and months. It's going to oxidize and go rancid on you.
Aha. And what was the dry matter equivalent of the flaxseed? Did you already talk about that?
The dry matter. They're asking for the dry matter percent of the flaxseed.
Yeah.
I can look it up. Keep talking.
Okay.
I'll pull the paper up and look. I'll have it here in a second. All this. It was in the 90s. We report organic matter of 96%, so it'd be a little bit lower than that. It was in the 90s.
Okay, great. I'm just going through it. I think we might have gone through all of these questions already. Do folks have other questions for Kathy? Oh, here comes some more. Did you see any milk fat depression from the higher feeding level of the flax?
Well, we've only fed it to fermenters, and fermenters don't milk, so we don't know yet.
Oh, right. So this is great.
Yeah.
Just a reminder that this is just starting.
Yeah. We're going to see where we will see that is with the research up at the University of New Hampshire, because we'll be able to feed different levels. With the on-farm stuff, we'll just be feeding one level, so we'll be basically comparing flax with no flax at whatever level we decide to feed. Still up for debate right now, probably going to be around 5–10%. We haven't settled on it. It won't be 15, but it might be 5 or 10%. But with the cows at UNH, we might be able to do something a little bit different, see if we do get some milk fat depression.
Okay. Any thoughts on sprouting flaxseed?
I haven't sprouted. I mean, we've done some work with sprouting the barley and some of the other ones. I don't know about some of the oil seeds. I haven't personally seen that done, but that's a good question. I don't know.
Okay.
I hadn't combined those two thoughts.
Yeah. For ongoing flax research, when do you expect to have the first public results, and where should we look for them?
We do try to get them out in the NODPA newsletter through press releases as it comes out. For the flax feeding, if I think we're planning on doing the first winter feeding study with UNH this coming winter, so it'll be the following year, next summer sometime till we get, because if we're not finishing up till say now, till we get all the samples analyzed, it'll be another year or so, unfortunately, and that's just the problem with research. It's not instantaneous.
So summer or fall of 2014.
Start looking, yeah. We should be starting to get some abstracts and some preliminary information out, I would think.
So through ODARI or NODPA or maybe even eOrganic, maybe we'll invite you back. I would love to have you back.
Sure. And we'll eventually do some fact sheets and things like that to put out.
Right.
You can put them up on your website and the Northeast Grazing Consortium website and some of the other grazing websites.
That's great. Do you have any idea of current flaxseed pricing?
I don't right now because we haven't bought it yet, so I haven't. We just got a very small batch for the fermenters. We only needed a couple pounds of it, so it's not really a realistic pricing. Somebody on here may know, and if they want to chime in, and if we have somebody who's selling and buying feed, I haven't looked at that yet. Yeah. I do encourage folks, if you do have a sense, just pop it into that question box. We'll spread the word here. And this is going back to molasses. So is molasses a waste product or a byproduct of another process? They missed the first part of the webinar. Yeah, a lot of it's I didn't say that directly. It's a byproduct of the sugar industry is where a lot of it comes from. That's why it's coming out of beet pulps, sugar beets and sugar cane and a lot of those types of products. Okay. And any other questions from our audience today? Okay. Okay, so let's see. Someone just said, okay, so if it's coming out of sugar beets, it's likely to be GMO-based molasses. I'm assuming that it's certified organic. If it's certified organic, yeah, it may be coming from organic sugarcane. Then I'd have to look at where we specifically got ours. The molasses we used was certified organic, so whatever source it came from a certified organic source. So no, that's a very good point. So I don't know what the organic sugar beet industry is. So you're getting way out of my realm. But we did use certified organic feed on certified organic cows, and not to say certified organic fermenters, but we did everything, organically there too. So I don't think we could certify our fermenters. This question says, is there a difference in the analysis between dried and liquid molasses? Do you know? I'd have to look it up specifically, but I think it's being used a lot more. The liquid is being used more, at least from the guys I'm seeing, because they're top dressing it on something, or they're using it as something else as a carrier for it. Whereas with the dried, I think they're probably going to lick it up, and it might be a cost factor. I'm not sure, or availability. I don't know. As far as availability or cost between the two, I'm not absolutely certain. When you don't have all that in front of you, I love questions I can't answer. It's going to make me go look it up. I'm just, someone has put in the price about flax. So the AMS Organic Feed Report has flax at $30.63. And they have a link, so I will just... For 100? They do not say. Okay. I'm just going to, but they have a little link here, so I'm just going to pop that right in the chat box there, so you can look that up. Let's see if that works. Yeah, so that'll give you a sense of prices there to refer to. Okay, so this question says, I'm not a vet, but in the human body, a high sugar level makes you susceptible to infections. Does this carry over to cows? Possibly, but we are absorbing the sugars directly, whereas we have that big box called the rumen that does all kinds of funky things to the feed, including the sugars that we feed them, because they are not absorbing the sugars directly. Those microbial bugs just attack those sugars and convert them into something else, including volatile fatty acids, including microbial protein, including into simpler sugars, so I don't know if it would have the exact same response. And we're not talking, it's not like we're feeding them, you know, lollipops and candy byproducts and high levels of that either. But I know what the person's saying, but with that rumen, I think there's some conversions, there may be some differences between ruminants and monogastrics like humans.
And are there other high sugar feeds that one might use instead of molasses and get the same effect?
In the conventional world, I'm sure there are. In the organic sector, it would depend on what's available, because that's where you know, our organic producers are so limited because they can't use a lot of the byproducts that others can use as well. But they're all going to vary. I mean, there's other high energy products, but they're going to vary because molasses also has a lot of minerals and some other things that the other ones may either have a different profile on or not as much of or even more of. So it's all going to vary. It's not just a one-to-one sugar substitution back and forth, because it's going to be the type of sugar and what else is in there as well.
So great. Well, thank you so much, Kathy. I really appreciate your time. As I mentioned before, you can find an archive of today's session, recordings of our other webinars, as well as articles, videos, and more at eextension.org/organic_production. And Kathy, thanks again for joining us.
Well, I appreciate the opportunity. It's always good to do.
I really appreciate it. And thank you all for coming.